Welcome to the third part of the essentials of the course Energy Supply for Buildings. In this third part you will learn about key characteristics of energy conversion systems for heat and cold. We will therefore address only the two first columns of this table describing the different ways of producing heat, cold and electricity. Electricity and waste heat are addressed in another lecture. Let's look into a bit more details into each of the energy conversion systems that were described in part 1, starting with combustion boilers. In a boiler, the air needed for combustion is supplied by a pipe, the white one below, and goes to the burner. In the burner, the fuel is burned and the fumes and flames give their heat to a heat exchanger where water is flowing. This heat exchanger will bring heat to the heating system of the building. There is a fan above expelling the fumes and combustion products like CO2 and CO to the outside through a pipe. As you may remind, these exhaust gases may have a temperature up to 150 degrees Celsius. This setup is known as being a non-condensing boiler. In a condensing boiler, an additional heat exchanger is placed, see here above in the exhaust pipes for the fumes, which give now also their heat to the cold water. Not only the fumes give heat back, also and mainly the water vapor contained in the fumes. This water vapor contains a lot of latent energy that is released when the vapor is cooled down enough to condensate. Of course, these droplets of condensed water must be drained out of the boiler through an additional pipe. So, with this condensation, much more heat is recovered from the burning process. The efficiency of non-condensing boilers is between 0.55 for the older ones and 0.85 for the modern ones. The efficiency of condensing boiler is much higher, up to 0.97. However, it is not because you buy a condensing boiler that it will work in condensing mode. To have it working in condensing mode, the temperature of the water in the heat exchanger should be below 55 degrees Celsius. In all heating systems that need a temperature higher than 55, the boiler will not work in condensing mode. Let's study the primary energy and resource depletion on the example of a building with a yearly heating demand of 3000 kWh and assume the heat is produced by a non-condensing gas boiler with efficiency 0.7 based on the higher heating value. The needed energy input is therefore 3000 divided by 0.7, which is 4286 kWh. Gas is a primary resource, therefore we can say that the primary energy consumption is 4286 kWh. But how much gas is that? We know from a former lecture that the energy content of North Sea gas, the higher heating value therefore, is 9.8 kWh per cubic meter. With this we can easily calculate the needed volume of gas, which is 4286 divided by 9.8 equals 437 cubic meter. And what about the CO2 emissions? We know from a former lecture that the CO2 emissions of natural gas are 0.2 kg CO2 equivalent per kilowatt-hour primary energy. The CO2 emissions are therefore 486 times 0.2 equals 857 kg CO2 equivalent. Let's now look at electrical heating. Basically, the principle of electrical heating is very simple. If electricity runs through a resistance like the one on the picture, it is fully converted to heat, meaning that the efficiency of an electrical heater is 1. That is what happens in your iron, for instance. There are 4 types of electrical heating systems. The ones that heat directly room air through convection, like this one. Second, the ones that mainly use radiative heat transfer, the so-called radiant or infrared panels. Third, the ones that heat a large water tank, either for space heating or for hot tap water heating. And finally, the ones used for instant hot tap water. They all use an electrical resistance like the one above. Let's take the same example of a building with an annual heating demand of 3000 kWh. If we use an electrical heater to produce this heat, we need, of course, 3000 kWh electricity because the efficiency is 1. But that is not the primary energy, because this electricity must be made somewhere in a power plant using natural resources. Let's consider that the electricity is produced in a gas power plant. The efficiency of such a power plant is around 0.4. So, the annual primary energy, representing the energy content of natural resources, is 3000 divided by 0.4, which is 7500 kWh. So, the true efficiency of electrical heating is not 1, but 0.4. And how much gas is that? Here too, using the energy content of 1 cubic meter of North Sea gas, which is 9.8 kWh, we come easily to a depleted volume of 765 cubic meter, almost 1.8 higher than with a gas boiler. As for the CO2 emissions, they are also 1.8 times higher. Clearly, electrical heating is not best. However, if the electricity was fully produced by non-combustible renewables like wind, photovoltaics or hydropower, there would be no CO2 emissions. The efficiency could be considered infinite, and we could consider the primary energy to be 0. The CO2 emissions would be 0 as well. So, in the end, the sustainability and environmental quality of electrical heating fully depends on the way electricity is produced. Heat pumps and chillers use environmental heat and also electricity. So, they can be classified as electrical systems as well, but much more efficient ones than the simple electrical resistance-based systems we have just described. A heat pump working in cooling mode is called a chiller. Air conditioners and refrigerators are chillers. Heat pumps and chillers make a clever use of the properties of liquid and gaseous substances, in particular the fact that the boiling temperature of a pure fluid depends on its pressure. The higher the pressure, the higher the boiling temperature. The boiling temperature is the temperature at which a liquid evaporates, but it is also the temperature at which vapor starts condensing. When a liquid evaporates, it takes heat from its environment. When a vapor condensates, it releases heat to the environment. A heat pump or chiller consists mainly of a closed pipe in which a refrigerant is circulating. One part of the pipe, the blue one, works at low pressure and the refrigerant evaporates there at a very low temperature, for instance minus 10 degrees, taking the heat it needs to evaporate, Q in evap, from its environment, air for instance, the so-called heat source. The second part of the pipe, the red one, works at high pressure, meaning that the refrigerant will condensate at a high temperature, 40 degrees for instance, releasing therefore high temperature heat to its environment, Q out cond. After condensation, the liquid refrigerant is expanded back to the low pressure through the valve on the right. After complete evaporation in the evaporator, the compressor brings the vapor to a high pressure. To do so, electricity, Q-elec, is needed to power the compressor, and the cycle goes on this way. When the cycle is optimized to produce heat at the condenser, we call it a heat pump. When the cycle is optimized to remove heat from the environment at the evaporator, we call it a chiller or air conditioner or a fridge. In all cases, because of the law of conservation of energy, the energy input to the heat pump, Q-elec plus Q in evap, equals the energy output, Q out cond. Let's look now at the efficiency of such a system. The efficiency of a heat pump is called COP, coefficient of performance. It is defined as the heat output divided by the electrical input. The heat taken from the heat source is for free as it is environmental heat. Note also that the COP can be expressed in terms of the ratio between the high temperature of the condenser in Kelvin and the difference between the low and high temperatures. The smaller the temperature difference Th minus Tc, the better the COP of the heat pump. That is why heat pumps perform better with low temperature heating like floor heating and high temperature sources, ground rather than cold outdoor air. See here some typical seasonal average values of COPs called SCOP for different heat sources. The efficiency of a chiller is called the energy efficiency ratio, EER, or sometimes cooling COP. It is defined as being the heat removed from the environment, Q in evap, divided by the electrical input to the compressor. The heat removed from the environment is the cold that is created in your fridge or in an air-conditioned room. Observe here too that for a high efficiency, Th minus Tc must also be as low as possible, which implies high temperature cooling and the possibility to reject the heat at a low temperature. Nowadays, air-to-air chillers can show an average seasonal EER of around 4, while a ground sink chiller could achieve an SEER of 30. Please also note that instead of using an electrical compressor, it is possible to use a waste heat-driven compressor in a so-called absorption chiller or heat pump. Let's finally look at the energy chain, taking again the example of a building having a heating demand of 3000 kWh. But this time we use a heat pump with seasonal COP 4, by which 3000 divided by 4 is 750 kWh electricity only is needed to power the compressor. If the electricity is produced by a gas power plant with efficiency 0.4, this leads to the use of 191 cubic meter gas and the emission of 375 kg CO2 equivalent, which is much less than with a gas boiler or with an electrical resistance heating. The calculations for a chiller would follow the same principle, using this time the cooling demand and the SEER instead of the heating demand and the SCOP. Let's look now at geothermal systems and consider that systems that do not go deeper than 200 meters are shallow ones. Let's start with the shallowest of them, earth tubes. Earth tubes are passive systems in which the outdoor ventilation air is circulating through pipes in the ground. The air is then heated by the ground, which in winter is warmer than the outdoor air. Next to this, there are also the ground heat exchangers used as heat source for heat pumps. You see them here in vertical and horizontal designs. They are connected to the evaporator of the heat pump. These systems work well when the warm season is long enough to regenerate the ground temperature. Then we have the systems based on aquifer thermal storage, which can only be used when the heating and cooling demands are well balanced and when there are suitable aquifers. An aquifer is a sand layer containing water. Let's start with the summer situation on the left, in which cooling is needed for the building, and just imagine we want to cool hot outdoor air from 35 degrees Celsius to 24 degrees. If we pump the cold water from the aquifer, we can easily transfer heat from the warm air to the aquifer water flowing through the heat exchanger. In this picture, I used aquifer water at 9 degrees, which is often the temperature in Northern Europe. So, the cold water from the aquifer is pumped and heated by the warm air up to 20 degrees in this example. This aquifer water at 20 degrees is then injected into the aquifer using a well placed far enough from the cold well, generally a few hundred meters. This pumping of the cold aquifer water is done all summer, resulting in a bubble of warm water at the warm well. As sand's thermal conductivity is not very high, the bubble of heat is able to remain for a few months. And then winter arrives, where we need heat. The heat that has been stored in the warm well can then be used by just reversing the flows in the heat exchanger. That's the picture on the right. Now the warm water is pumped to the heat exchanger, in which it gives its heat to the cold outdoor ventilation air in such a way that it is nicely preheated, for instance from 5 degrees to 15 degrees. In general, there are temperature limitations, and for instance in the Netherlands it is forbidden to use warm well temperatures above 25 degrees. It is also mandatory to make sure and demonstrate that there is a thermal balance in the ground, meaning that the quantity of heat extracted is the same as the quantity of heat supplied to the ground. Be aware that these systems in fact do not even use the heat from the ground. They just store cold and heat from the building and the outdoor air. And finally, we have deep geothermal energy, which is thermal energy generated in the core of Earth. Just like for the aquifer thermal storage, all water or steam that is extracted should be refilled in order to maintain the geological balance and to not induce pressure differences that could lead to earthquakes. In the picture, you see such a geothermal plant with two wells to extract warm water and one to re-inject it. In the heat exchanger above the ground, the hot groundwater or steam gives its heat to a hot water distribution pipe connected to district heating. Such geothermal systems can provide water at 40 to 70 degrees like in the Netherlands, but also at much higher temperatures like in Iceland and many other places all over the world. When the temperature is above 100 degrees Celsius, it is even possible to use the steam to produce electricity, which we will treat later. The concurrent production of heat and electricity makes such a system much more affordable. Such a geothermal system is relatively expensive, and these systems are generally used to heat complete districts or cities and are never used solely at building level. In terms of primary energy and CO2 emissions, earth tubes, ATES and deep geothermal systems require pumping power. The electricity needed for the pumps may be significant, especially in the deep geothermal systems. However, this electricity represents only a small fraction of the resources and CO2 emissions that are produced when using combustion boilers or electrical resistance heating. In most national codes, geothermal heat is just considered to use zero primary energy and to have zero CO2 emissions. What about environmental cold? In the precedent slide, we already looked at ATES systems as a way to use cold of the ground or to store it in the ground. Earth tubes can also be used for the cooling of ventilation air. In general, the shallow ground is colder than outdoor air during the hot season. There are therefore passive systems making use of this by circulating the outdoor ventilation air through pipes in the ground. Instead of the ground, it is also possible to use surface water like a pond, a river, a lake or a sea. Their temperature is generally lower than the outdoor air temperature during summer. For instance, river water can be used to cool indoor air using a heat exchanger. In many countries, there are regulations about the maximum temperature at which the water is re-injected into the river, lake or sea. This maximum temperature is around 25 degrees or even lower, limiting this way the available power. The aim is to protect the fauna and flora in water, which could be harmed by too high temperatures. Finally, we can use evaporative cooling to cool air. Evaporative cooling is possible due to the ability of water to evaporate in air when the air is not saturated. You have learned that water evaporates at 100 degrees Celsius at atmospheric pressure, which is 1 bar. At lower pressures, the evaporation temperature of water is much lower. See the red rectangle in the picture. Air is a mixture of different gases, including water. The partial pressure of water in air is very low, by which it can evaporate at outdoor temperature. And you also have learned that when a fluid is evaporating, it takes a lot of heat from its environment. So, if you inject water droplets in air, it will automatically evaporate because of the low partial pressure, and by evaporating, it will take the needed heat of evaporation from the air, which therefore will cool down. That is the principle on which evaporative cooling is based. You see here a few examples of evaporative cooling. Left, a very simple, not very effective home system with just a water container and a small fan. Then a mist machine, often used outdoor to cool a bit hot, warm outdoor air. Finally, a picture of a wind catcher in Iran. When used in combination with a fountain or a spray, see figure below, it is quite effective in cooling warm, dry air. Evaporative cooling is very efficient in terms of energy usage, and we can by approximation neglect the energy use of the pump, by which primary energy and CO2 emissions are zero. However, it is not applicable in humid countries as the air there is already close to saturation. Finally, let's look at solar energy. Solar thermal collectors is the name we use when only heat is produced and no electricity. It's just a water pipe, by preference black, to absorb as much as possible solar radiation. The water comes cold in at TW1 and is heated directly by the absorbed solar radiation to TW2. To limit the heat losses, it is quite important to insulate well the backside of the collector and to place a glass cover above the pipe, preferably glass, with a high transmission factor in the light spectrum. To deal with the intermittency of solar radiation, we can use a storage tank and fill it with hot water when the sun shines. In a system with a tank, cold water is fed underneath and a heat exchanger with water coming from the collector heats the water. Warm water rises so the outlet pipe to the taps is located above. Real simple and effective. If the application is for hot tap water rather than for space heating, care has to be taken that, especially in large tanks, the water can be heated once a week to 65 degrees to kill the Legionella bacteria. If that is not possible with the solar collector, an additional electrical resistance can be used. In colder countries, such a solar boiler is even combined with additional heating by either a combustion or electrical boiler. There are many ways to improve the efficiency of the simple solar collectors. For instance, vacuum collectors have much higher efficiency. Concentrating collectors concentrate the solar radiation on the water pipe. It collects this way radiation that would otherwise fall at another place and can concentrate the radiation up to 100 times. Very high powers can be achieved this way. In fact, the power may be so large that temperatures far above 100 degrees are achieved, by which steam is produced and drives a steam turbine. So, electricity can be made from solar heat. But there are many other relevant applications. The warm water from the solar collector can be used as heat source for heat pumps or to regenerate the ground temperature when a ground source heat pump is used or an ETS system are used. It can also be used as source for low temperature heating networks, so there are plenty of useful applications in development. This brings us to the end of this lecture on energy supply for heating and cooling buildings. In part 4, energy systems for the production of electricity will be addressed. Thank you for your attention.